Hello everyone, here I present an interesting problem before you. Suppose I have a steel utensil and I tie up a flexible thread, and now I want to hang the steel utensil by just making few number of turns of the rope like this. So what do you think? How many turns do we require to hang the steel utensil like this? Think about it and post your answer in comment box. I am reducing the number of turns. Just pay attention. Okay, nothing is happening. Reducing further more one turn. Yet nothing is happening, and reducing the next turn and it goes down. Okay, it slides down. You might be tempted that this steel utensil might have less weight, so I am able to hang it. Let me bring some other massive object and retry this experiment. This time I have heavy iron utensil, and what do you think? Will we be able to balance this heavy iron utensil as previously we balanced the steel utensil? What is your opinion? Just keep watching and see the interesting thing yourself. So, I am able to hang up this heavy iron utensil, and I have not placed the knot of the thread here. Okay, just few number of turns are there. So, can you explain the physics behind this? There are many more such incidents in daily life. If you have seen the churning of the curd, the Bologna method of making the ghee, I'll present it at the end of this video, where again I'll be demonstrating this thing. Okay, I'm reducing the number of turns and see the effect. Nothing happens. Reducing the number of turns and then it goes down. Okay, let's explore the beautiful physics behind this. Suppose here we have a fixed curved surface and a rope passes over the surface. The angle of contact of the rope with the fixed curved surface is theta, and the coefficient of friction between the curved surface and this rope is mu. Got it? Okay. And the radius here we are taking up as r. The motion or the impending motion of the rope we are assuming in this direction, and I am naming the tension here as T2 as well as the tension here as T1. Obviously the T2 will be greater than T1. Why? In order to explain it, I am making the free body diagram. Suppose this is the rope. Here we consider that angle theta. At every contact point of the rope and this surface, the normal will be in a different direction. Suppose if you show the normal here, then it will be shown like this, dn. If you show the normal here at this contact point of the rope and the fixed surface, then the normal dn will be shown like this. You may consider other points of the surface. Take the radial directions. Here the dn will be like this, and here the dn will be like this. So actually at every contact point, the distribution of the normal is unknown to us. Same happens with the friction. The impending motion or the tendency of motion or the actual motion is in this direction. Then the friction on the rope will be acting like this. So I am showing that friction here. At this point, the friction will be shown like this. Same you can do for other points. If we look at this tension T2, it has to overcome the effect of the friction acting and the tension T1. Then obviously the T2 should be greater than T1. Got it? Now we are going to prove that T2 is equal to T1 e to power mu theta. Let's see the derivation here. Here is the fixed contact surface. The rope lies from here to here. Okay. And this angle has been taken as theta. I am taking up a very small element of the rope like this. This much small element of the rope has been considered for the derivation purpose, because at every contact point of the rope with the fixed surface, the friction and the normals distribution is very complex, unknown to us. So we'll start with a small element. We consider the angle here to be alpha, and this much angle is d alpha. So at the angle alpha, I show the tension in this small element as T, and at the angle alpha plus d alpha, we show the tension as T plus dt. The element of the rope has the tendency of sliding in this direction, and in order to oppose that tendency of the sliding, the friction will be acting like this. Do you agree? On the element of the rope, the friction will be acting like this. We are taking up the case of the impending motion. So the friction will be mu times dn, where dn is the normal force acting on this element of the rope. Got all these things? Now let us pay attention again. This vertical line and these horizontal lines, I am making up few angles, you pay attention. What will be this angle? This will be d alpha by 2. Similarly, what will be this angle? It will also be d alpha by 2. Check this angle. This will be d alpha by 2. Similarly, check this angle. This will also be d alpha by 2. I am writing the angles here. This angle is d alpha by 2. Similarly, this angle is also d alpha by 2. And doing the components of the tension. The component of tension here will be T cos d alpha by 2. Do you agree with that? And component here will be T sin d alpha by 2. Similarly, we are doing components here. The component in this direction will be T plus dt cos of d alpha by 2. And the component here in this direction will be T plus dt sine of d alpha by 2. Since we are taking up the case of the impending motion, I am balancing up the forces in x direction and y direction. We consider this as the x direction for our computation, this as the y direction. First of all, I am making sigma fx is equal to 0. Pay attention what we should be writing. In x direction, we have the force here T plus dt cos d alpha by 2 is equal to mu dn plus T cos d alpha by 2. Check it yourself. One horizontal force in this direction, two horizontal forces in this direction, they should cancel out each other to make the sigma fx 0. Got it? Here we know one thing, for very small angles, actually d alpha is very small angle. So for very small angles, there are the approximation in the trigonometry. So using the approximation here, what we should be writing, T plus dt cos d alpha by 2, it will be taken as 1 is equal to mu dn T cos d alpha by 2. So cos d alpha by 2, this will become 1 for very small angle that happens. Okay, let's go further. This is an equation which we can simplify. This t and this t will get cancelled out. So finally we are left with dt is equal to mu times dn. We call it equation number 1. Now we are balancing the forces in y direction. Sigma fy must be equal to 0. So here is a force dn and here are the forces T plus dt sine d alpha by 2 plus T sine d alpha by 2. Do you agree with this? Going further for the computation and taking the approximation. For very small angle, sine d alpha by 2 can be written as d alpha by 2. Same we can do here. So the dn will be equal to what? T plus dt d alpha by 2 plus t multiplied with d alpha by 2. We can simplify this expression further. It is t d alpha by 2 t d alpha by 2. So t into d alpha. You understand this computation? T d alpha by 2 t d alpha by 2. 2 times when you operate it, it will become t d alpha. Plus we are left with dt d alpha by 2. dt d alpha by 2. Here are two infinitesimals which are in multiplication. If we have two very small quantities in multiplication with respect to the first order infinitesimals, their product will be negligible. So actually this term is neglected. This is tending to 0. Got it? So what we are left with, dn is equal to td alpha. This is the second equation I wish to write. dn is equal to td alpha. Call it equation number 2. Okay. Now simplifying the equation 1 and 2, will be getting our final answer. Once you should note it down up to here, then I'll clear up some space and will obtain the final result. From equation 1 and 2, we can write dt is equal to mu t d alpha. I hope you get this. Now dt by t can be written as mu times d alpha. We can integrate both sides. When the angle alpha is 0, alpha got started from here. When the angle alpha is 0, we have taken the tension as T1. Got this limit? So I am putting here T1. When the angle alpha becomes equal to theta, then we have taken the tension as T2. So writing that limit here, I hope you understand this integration. I am writing directly. It will be log base E T2 by T1, and here will be getting up mu theta. Simple and easy answer. And now we are taking up anti-log both sides. So the result will be T2 by T1 is equal to E2 power mu theta. And this result can be further expressed as T2 is equal to T1 E2 power mu theta. Now T2 here is the maximum tension, T1 here is the minimum tension, the lower tension in this rope. Okay. And E is the Euler's number 2.7183, mu is the coefficient of friction, and theta is the total angle of contact of the rope or belt with the fixed surface, and theta must be expressed in radians. Okay, I'll write all these details on the next page for your convenience. Let us see few more important things. In this entire derivation, the r appears nowhere. It means the radius of the curvature of this surface is of no use in this derivation. So the curved surface might be even irregular. Okay, the rope might be passing on irregular surface. Even then this result is valid, as the radius r appears nowhere. Got it? Another important thing, suppose if rope is making n tons over a cylinder, over a drum, then the theta will be equal to what? 2 pi multiplied with the n. Got it? Let us write all these important results on the next screen for better understanding. And if you have any doubt in this derivation, fire up the comment box. I'll reply. So here are the important notes of this derivation, and if you want all of them in the form of a PDF, you may visit our Telegram channel. And if you liked this video, let me know in the comment box, and please like, share and subscribe. Okay, after this I'll be taking up a question to demonstrate the power of the equation what we have derived right now. T2 is equal to T1 e2 power mu theta. Till then you may take down these notes. Here lies an interesting question for the practice. If you wish, you may pause the video here and give it a try, and then please post your answers in the comment box. After that, I'll be simplifying this problem on the board. Give it your best shot. I hope you are done with your calculations. So let's check up the answer here. Here lies the rod and the rope passes like this. Here is the first turn, here lies the second turn, and then another half turn. Okay. The cylinder hangs here, and cylinder is actually stationary as given in the question. So I am showing up the forces on the cylinder first. Its mg will be equal to 20g, and here will be some tension which we say as T2. Cylinder is actually at rest. It has been prevented from descending down. If cylinder is at rest, then we can directly say that T2 should be equal to 20g. Got it? Now, here was some force applied, which we write as T1 is equal to 25 Newton. In our original derivation, you might remember that T2 is equal to T1 e2 power mu theta, which was greater. The T2 or the T1? The T2 was greater, and here the T2 is greater as compared to T1. I have another logic to classify the T2 and T1. The cylinder has a tendency of sliding down. Check the initial lines of the question, the first line of the question. Cylinder has a tendency of sliding down like this. Means this rope wants to slide like this in this direction. I'll indicate impending motion by the green color. You get it? The impending motion of rope is like this. So the friction on the rope will be acting in the opposite direction. Now the tension here has to balance this friction as well as this T1. I am repeating it. Tension here in the rope has to balance this friction as well as this tension. Obviously, this tension should be higher. So the T2 is greater than T1. Got it? I am utilizing it, putting up the data. How much is T2? T2 is 20g. How much is T1 with us? It is 25. E and then mu is unknown, and keep theta as theta, although we know the value of theta. If there are n turns, then theta is equal to what? 2 pi n. You remember that? And how many turns do we have here? N is equal to 2.5. So the theta will be equal to 2 pi into 2.5. Got it? I am naming it equation number 1. Any doubt in this? Okay. Now taking up the diagram for case number 2. Call it case 1. And here I am making the diagram for case 2. Same rod, same number of turns, same rope. So 1 turn, 2 turn and the half turn. The cylinder hangs here. The 20g is the weight of the cylinder. This time here I'll call the tension as T1, and this is the force F, which we take as T2. Why so? If you check the language in the second case, the cylinder has to go up. There is a tendency of going up. Okay, the minimum force required. So the cylinder has a tendency to go up. If cylinder has a tendency to go up, where is the impending motion of rope in this case? If we check in this direction, there will be the impending motion of rope. Do you agree? If the impending motion of the rope is in this direction, it means the friction acting on the rope will be like this. The tension here has to counter this friction as well as this tension. So obviously the T2 should be higher tension. Got it? So this time what will be the equation? F should be equal to 20G, or this tension T1, whatever you write, e to power mu theta. Got it? I'm using this equation. T2 is equal to T1 e to power mu theta. Cylinder is yet at rest. It has just a tendency to go up, and T1 will be equal to mg. So I have taken the T1 is equal to 20G. Now we have two equations, equation 1 and equation 2. From these two equations, we have to figure out the value of F. It is pretty easy. Can we obtain e to power mu theta from first expression? It can be written as 20G divided by 25. So put the value of e to power mu theta from equation 1. Take G is equal to 9.81 meter per second square and do your computation. You will get the value of F. And now I'll be presenting few problems for your practice. Hey, today I'm churning out the curd for making ghee. So what do you think? What is better here? Less number of tons or more number of tons? Let me know about your opinion in the comment box. And if your answers are correct, I'll be sending you the fresh ghee. Stay awesome, stay healthy. Take care. Bye-bye.